welcome to this problem walkthrough. Today, we're diving into problem number 2134, minimum swaps to group all ones together too. In this problem, we'll explore how to efficiently group all ones in a circular array with the minimum number of swaps. Let's get started. In this problem, we're tasked with working on a binary circular array called data. This array consists only of zeros and ones, and being circular means that the first element is considered adjacent to the last element. Our goal is to determine the minimum number of swaps required to group all the ones together in any location within the array. For the input, we receive a list of integers representing this binary circular array, and the length of the array is denoted as n. The output is a single integer representing the minimum number of swaps necessary. This setup challenges us to think about how to efficiently group all the ones while accounting for the circular nature of the array. Let's look at the first example to understand the problem better. The input array is 0, 1, 0, 1, 1, 0, 0. This array contains 3 ones in total. To group all the ones together, we need to consider a sliding window of size 3, which matches the total count of ones. One possible way to achieve this grouping is by swapping the 1 at index 1 with the 0 at index 2. After this swap, the array transforms into 0, 0, 1, 1, 1, 0, 0. As we see, this grouping requires only one swap, so the output for this input is 1. This example highlights the use of sliding windows and the importance of identifying the optimal way to group the ones with minimal swaps. Now, consider the second example where the input array is 1, 1, 0, 0, 1. In this case, all the ones are already grouped together at the very beginning of the array. Since no swaps are needed to achieve the grouping, the output here is simply 0. On the other hand, in the third example, the input array is 1, 0, 1, 0, 1, 0, 0, 1. This array contains 4 ones, so we use a window of size 4 and slide it across the circular array to calculate the minimum swaps. One optimal solution is to group the ones at indices 4, 5, 6, and 7. To achieve this, we need 2 swaps, making the output for this example 2. These examples demonstrate different scenarios and edge cases for grouping the ones together. Finally, let's talk about the constraints and edge cases. The length of the array, n, can range from 1 to 100,000, so our solution must be efficient, ideally with a time complexity of O, n. Each element in the array, data, I, can only be either 0 or 1. For edge cases, if the array contains only zeros, the output is always 0 because no swaps are possible. Similarly, if the array consists entirely of ones, the output is also 0 since the ones are already grouped. For smaller arrays, such as those with fewer than 3 elements, we must ensure the solution handles cases like 1, 0, or 0, 1 correctly. Lastly, for large arrays, the algorithm must be optimized to handle up to 100,000 elements efficiently, ensuring that it performs well even for the upper limit of the constraints. To start, we considered a brute force approach. The idea here is straightforward. Since the array is circular, we can examine every possible segment of the array that has a length equal to the total number of ones, which we'll call count_ones. For each of these segments, we calculate how many swaps are needed to bring all the ones together within that segment. To handle the circular nature of the problem, we create an extended version of the array by concatenating the array to itself. This allows us to simulate circularity and check segments that wrap around. While this approach is simple to understand, it involves iterating over all possible segments of the array, leading to a nested loop structure. This results in a time complexity of O, n*k, where n is the size of the array and k is the number of ones. Additionally, the space complexity is O, n, due to the extended array. The main drawback of this approach is its inefficiency on larger arrays, particularly when count_ones is large, making it impractical for real-time scenarios. Next, we have the sliding window approach, which significantly optimizes the process. Instead of recalculating the number of swaps for every segment, we use a sliding window technique to efficiently count the number of zeros in each window of size count_ones. This eliminates redundant calculations and saves computation time. The key insight here is that the problem can be reframed as finding a window of size count_ones that contains the maximum number of ones, or equivalently, the minimum number of zeros. To handle the circular nature of the array, we extend it by concatenating it to itself, just as in the brute force approach. Then, using a sliding window of size count_1's, we calculate the count of zeros. For the first window, we count the zeros directly. As the window slides, we simply update the count by adding the value of the incoming element and removing the value of the outgoing element. This avoids recalculating the count from scratch for each window. As we slide through the extended array, we track the minimum number of zeros encountered, which directly corresponds to the minimum swaps needed to group all the ones together. The sliding window approach shines in terms of efficiency. Its time complexity is linear, O(n), where n is the size of the array, since each element is processed at most twice, once when it enters the window and once when it leaves. The space complexity remains O(n) due to the extended array. Compared to the brute force method, this approach is highly efficient for large arrays and avoids redundant calculations. While we also considered alternative methods, like the prefix sum approach, it doesn't provide any clear advantage in terms of time complexity or simplicity over the sliding window technique. Another option was a greedy approach, where we would attempt to modify the array in place to minimize swaps. However, this strategy becomes complicated when dealing with the circular nature of the array, and the potential for error increases significantly. Therefore, while these alternatives might be worth exploring in other contexts, they don't offer the same balance of efficiency and straightforward implementation as the sliding window method. Ultimately, we selected the sliding window approach as the most effective strategy. It combines efficiency with simplicity, making it well suited for this problem. The method's ability to reuse calculations eliminates redundancy and ensures that the solution runs in linear time. This makes it a clear improvement over the brute force approach, which is computationally expensive. The prefix sum method, while valid, doesn't offer additional benefits over sliding windows, and the greedy approach introduces unnecessary complexity when handling circular arrays. By leveraging the sliding window technique, we achieve an optimal balance of clarity, correctness, and performance, making it the ideal solution for minimizing swaps to group all ones together in a circular array. The problem involves a binary array that behaves in a circular manner. Our goal is to determine the minimum number of adjacent swaps required to group all the ones together in the array. Now, one way to approach this is through a brute force method. First, we calculate the total number of ones in the array, which we'll call count_1's. If count_1's is 0, or if it equals the length of the array, no swaps are necessary, so we can return 0 immediately. Next, since the array is circular, we simulate this circular property by creating an extended version of the array. This extended array is formed by appending the original array to itself, allowing us to treat any circular segment as if it were linear, which simplifies the problem significantly. Now that we have the extended array, the next step is to evaluate all possible contiguous segments of size count_1's within it. For each segment, we calculate the number of zeros, as this value represents the number of swaps required to group all the ones together in that segment. To efficiently process these segments, we use a sliding window technique. First, we calculate the number of zeros in the initial window of size count_1's. Then, as we slide the window across the extended array, we update the count of zeros dynamically by adding the new element entering the window and removing the element that is leaving. By doing this, we avoid recalculating the count of zeros from scratch for each segment. Throughout this process, we track the minimum number of zeros encountered, which ultimately gives us the minimum number of swaps required. Several key insights make this approach efficient. First, by extending the array, we handle its circular nature seamlessly without the need for complex modular arithmetic. Second, the sliding window technique significantly optimizes the traversal of segments, as it allows us to update the count of zeros in constant time rather than recomputing it for every segment. Finally, the number of swaps required to group all ones in any segment is directly equivalent to the number of zeros in that segment, simplifying the logic. In terms of data structures, the extended array facilitates the handling of circular behavior, while the sliding window ensures efficient computation. When analyzing complexity, the algorithm runs in O(n) time, with one pass to count the ones and another to process the sliding window. The space complexity is O(n) due to the extended array, but this can be considered efficient given the problem constraints. Let's consider an example to understand the process clearly. Suppose the input array is 1, 0, 1, 0, 1. First, we count the ones, which gives us count_1s equals 3. Next, we construct the extended array, which becomes 1, 0, 1, 0, 1, 1, 0, 1, 0, 1. Using a sliding window of size 3, we evaluate each segment. The first segment, 1, 0, 1, contains 1 0, meaning one swap is needed. The next segment, 0, 1, 0, contains 2 zeros, requiring 2 swaps. Moving to the next segment, 1, 0, 1, we again find 1 0, needing 1 swap. The minimum swaps out of these is 1, which is our answer. For edge cases, if the array contains all zeros or all ones, no swaps are needed since the ones are either absent or already grouped. For very small arrays, such as size 1, no swaps are necessary either. While modular arithmetic could replace the extended array, using the extended array simplifies the implementation and avoids unnecessary complexity. The sliding window ensures the algorithm remains efficient and easy to implement, making this approach both practical and elegant. Here, we begin by defining the function minswaps within a class called solution. The first step is to calculate the total number of ones in the input array nums using the sum function, which we store in the variable count_ones. This value represents the number of ones that we need to group together. Next, we handle an edge case. If there are no ones in the array or if the entire array consists of ones, no swaps are necessary, so we return 0 immediately. After addressing this edge case, we extend the array by concatenating it with itself. This allows us to simulate circular behavior, which is crucial for solving the problem efficiently. Now, we need to determine the maximum number of ones that can fit within a window of size count_ones. To do this, we initialize a sliding window. First, we calculate the number of ones in the initial window by summing the first count_ones elements of the extended array. We store this sum in current_ones and also initialize max_ones_in_ window with this value. This setup prepares us to slide the window across the extended array in the next step. Now, we slide the window across the extended array to determine the maximum number of ones that can fit within any valid window of size count_ones. For each step, we update the current_ones by adding the next element in the window and subtracting the element that just moved out of the window. This efficiently keeps track of the number of ones in the current window without recalculating the sum from scratch. We also update max_ones_in_ window to ensure it always reflects the largest number of ones observed in any valid window so far. Finally, the minimum number of swaps required to group all ones together can be calculated as the difference between the total number of ones, count_ones, and the maximum number of ones found in a valid window, max_ones_in_ window. This result is then returned as the output of the function. Here, we begin by defining our solution class and the method minswaps, which takes an integer array nums as input. The first step is to calculate the total number of ones in the array, which we store in the variable count_ones. This is done using a simple loop that iterates through each element in the array and adds the value to count_ones. This count is crucial because it determines the size of the window we will use later in the algorithm. Next, we handle two edge cases. If the array contains number ones, or all its elements are ones, no swaps are needed to group them together, so we can directly return 0. Now, we move on to setting up a sliding window approach. The goal of this sliding window is to find the maximum number of ones that can fit into a window of size count_ones. We initialize two variables, max_ones in window to keep track of the maximum number of ones we find in any window, and current_ones to count the number of ones in the current window. To simulate the circular nature of the array, we extend the array virtually by looping through it twice. If the current index is within the size of the initial window, we simply add the value at nums, i%n, to current_ones. At this stage, we also set max_ones in window to equal current_ones as a starting point for comparison. Once the initial window is processed, we begin sliding the window one step at a time. For each new step, we add the next element in the array, accessed using nums, i%n, to current_ones. Simultaneously, we remove the element that is falling out of the window, which is accessed using nums, i_count_ones%n. This ensures that the window always contains exactly count_ones elements. After updating current ones, we compare it with max ones in window and update max ones in window if the new count is higher. This process continues as we slide through the extended array. Finally, once we have determined the maximum number of ones that can be grouped in any valid window, the minimum number of swaps required is simply the difference between the total count of ones stored in count ones and max ones in window. This difference represents the number of zeros in the best window that need to be swapped with ones to achieve the grouping. The method then returns this value as the result. We start with the given input array, nums, which is 1, 0, 1, 0, 1, 1, 0, 1. The first step is to calculate the total number of ones in the array, which is 5. Since the problem involves treating the array as circular, we extend the array by appending it to itself. This gives us the extended version of nums, 1, 0, 1, 0, 1, 1, 0, 1, 1, 0, 1, 0, 1, 1, 0, 1. Next, we initialize a sliding window with a size equal to the count of ones, which is 5. Looking at the first window, nums, 0:5, the sum of elements is 3, since there are 3 ones in this segment. We also set an initial value for the maximum number of ones found in any window, max_ones_n_window, which starts at 3. Now, we slide the window across the extended array to evaluate other segments. For the first slide, from window 1:6, we add nums, 5, which is a 1, and remove nums, 0, also a 1. The total number of ones in the window remains 3. For window 2:7, we add nums, 6, which is a 0, and remove nums, 1, also a 0, so the count remains 3. In window 3:8, we add nums, 7, a 1, and remove nums, 2, another 1, so the count is still 3. However, in window 4:9, when we add nums, 8, 1, and remove nums, 3, 0, the count increases to 4. At this point, we update max_ones_n_window to 4, since it's now the highest count we've seen. Lastly, in window 5:10, adding nums, 9, 0, and removing nums, 4, 1, decreases the count back to 3. With max_ones_n_window finalized at 4, we calculate the minimum swaps required as count_ones minus max_ones_n_window, which is 5 minus 4 is equal to 1. So, the output for this example is 1. In this example, the input array is nums equals 0, 0, 0, 1, 0, 1, 1, 0. First, we calculate the total number of ones, which is 3. To simulate circularity, we extend the array, resulting in nums equals 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 1, 1, 0. The sliding window size is equal to count_ones, which is 3. Looking at the first window, nums, 0:3, there are number ones, so the sum is 0. We initialize max_ones_n_window to 0, as no window so far contains any ones. We now slide the window through the extended array to find the maximum number of ones in any segment. In window 1:4, we add nums, 3, a 1, and remove nums, 0, a 0, resulting in 1 1 in the window. For window 2:5, we add nums, 4, a 0, and remove nums, 1, another 0, so the count remains 1. In window 3:6, adding nums, 5, which is a 1, and removing nums, 2, a 0, increases the count to 2. For window 4:7, we add nums, 6, another 1, and remove nums, 3, also a 1, so the count stays at 2. Finally, in window 5:8, adding nums, 7, a 0, and removing nums, 4, also a 0, keeps the count at 2. The highest number of ones in any window is 2, so max_ones_n_window is updated to 2. Using the formula count_ones minus max_ones_n_window, we have 3 minus 2 is equal to 1. Therefore, the output for this example is also 1. In this case, the input array is nums equals 1, 1, 1, 1, 1. Here, the total number of ones, count_ones, is 5, and since every element in the array is already a 1, no swaps are needed to group all the ones together. As a result, the minimum swaps required is 0. The output for this example is simply 0. Here, we analyze the time complexity of the solution, which primarily relies on the sliding window technique applied to an extended version of the input array. First, summing all the ones in the array takes O, n, where n is the size of the original array. This is because the sum, nums, operation simply iterates through the array once. Next, the array is extended to simulate circularity by concatenating it with itself, resulting in an operation that also takes n, as it creates a new array of size 2n. Finally, the initialization of the sliding window involves calculating the sum of 1's in the first count_1's elements. Since count_1's can be at most n, this step is also bounded by n. These steps set the foundation for the sliding window process. The sliding window is then applied to the extended array, iterating through indices from count_1's to 2n1. During each iteration, we update the window sum and compare values, and since each update takes constant time, the total time for this step is proportional to the number of iterations, which is 2n count_1's. In the worst-case scenario, count_1's is small, so this simplifies to 2n, which is equivalent to n. When we combine the time spent on summing the array, extending it, initializing the window, and sliding it, we get n plus n plus n plus n, which simplifies to n. This establishes that the overall time complexity of the algorithm remains n. Now, let's examine the space complexity. The largest contributor is the input array extension, where the original array is doubled in size to simulate circularity. This requires additional memory proportional to the size of the array, resulting in n space. Beyond this, the algorithm uses a constant number of auxiliary variables to manage computations, such as count_1's and current_1's. These variables don't depend on the size of the input and therefore contribute 1 to space complexity. When we combine these factors, the total space complexity becomes n for the extended array plus 1 for the auxiliary variables, which simplifies to n. When comparing the sliding window approach to a naive or brute force method, the efficiency gains become clear. A brute force solution would involve generating all possible subarrays of size count_1's in a circular array. This process takes n squared iterations, and counting the number of 1's in each subarray would add another n in the worst case, resulting in a total time complexity of n cubed. In contrast, the sliding window method avoids recalculating the sum for each window by reusing calculations from the previous window. This optimization reduces the time complexity to n, making it far more efficient than the brute force approach. Finally, let's break down the best, average, and worst-case scenarios. In the best case, all the 1's are already grouped together, and the algorithm only needs to compute the sum of the array, which takes n. In the average case, the algorithm processes the array and applies the sliding window technique, resulting in n time complexity. Even in the worst case, where everyone is separated by zeros, the sliding window still processes the extended array in n time. To validate this, consider that the sliding window iterates over the extended array of size 2n, performing a constant amount of work per element. This directly leads to a time complexity of n. The space complexity is similarly n, dominated by the extended array, confirming that the algorithm remains efficient in all cases. When working with this problem, there are a few common mistakes to watch out for. First, forgetting the circular nature of the array is a frequent error. This happens when you treat the array as if it ends after the last element, without considering wraparound segments. Since the array is circular, you need to use modulo arithmetic to handle indices that go beyond its length. Ignoring this can lead to incomplete or incorrect solutions. Another frequent issue is implementing the sliding window incorrectly. Specifically, failing to update the window bounds properly in a circular context can cause errors, especially when the window needs to span from the end of the array back to the beginning. Additionally, some people forget to optimize their solution by pre-computing key values, such as the number of 1's in the array. Recomputing this information repeatedly for each segment increases the time complexity unnecessarily, particularly when working with large inputs. Instead, using techniques like a running sum or a prefix sum can make your solution far more efficient. Another area where mistakes often occur is in handling edge cases. For example, failing to consider arrays that contain all 1's, no 1's, or very small sizes can lead to issues like division by zero errors or incorrect results. Special cases like these should always be accounted for to ensure the solution is robust. Additionally, misinterpreting the problem statement can be a major pitfall. Some people confuse minimum swaps with other operations like minimum moves, which leads to developing an entirely incorrect approach. Taking the time to carefully read and understand what the problem is asking for is essential to avoid wasting time on the wrong solution. Now, let's consider some key insights that can help you excel in solving this problem, especially in an interview setting. First, whenever you deal with circular arrays, modular arithmetic becomes critical for handling wraparounds. Interviewers often expect you to explain how you manage indices that go beyond the array length, so be prepared to discuss that. Second, the sliding window pattern is a powerful tool for solving subarray problems like this one. Practicing its implementation will help you use it efficiently and intuitively. Another important insight is that problems involving minimum swaps or minimum moves often reduce to identifying an optimal segment where a certain property, like grouping all ones, is satisfied. Recognizing this can simplify the problem significantly. Finally, asking clarifying questions about edge cases is crucial during interviews. For example, you might ask, what should the output be if the array contains no ones or is very small? Such questions demonstrate your analytical thinking and attention to detail. If you're interested in related problems to practice, you can check out challenges like LeetCode 567, 76, 239, or 3, all of which use similar techniques such as sliding windows and subarray optimizations. To wrap up, let's briefly discuss some alternative approaches to solving this problem. The brute force method involves checking every possible segment of length equal to the number of ones in the array and calculating the number of swaps needed for each segment. While this approach is simple to implement, it has a time complexity of O in superscript 2, making it impractical for large inputs. A more efficient alternative is the sliding window technique, where you use a fixed size window of length equal to the count of ones and track the number of ones in each segment. This method has a time complexity of O, n, but requires careful handling of circular indices to account for the array's wraparound nature. Another option is the prefix sum approach, where you pre-compute the prefix sums to quickly calculate the number of ones in any segment. Although this method requires additional space for the prefix sum array, it simplifies the implementation of range queries and can be a good choice depending on the problem constraints. Each of these methods has its trade-offs, so understanding their strengths and weaknesses is key to selecting the right one for your specific use case. Great job making it to the end. In this walkthrough, we reviewed how to group all ones in a circular array with the minimum swaps. We covered key concepts like using sliding window techniques and handling circular arrays effectively. Thanks for watching, and stay tuned for more coding problems and solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!